Okay, so we'll continue on this topic of optimization. Whatever. I don't know. Yeah, sure. Okay, so we're gonna have optimization, and then one application to maximum likelihood estimation. Okay. And what we say is that, our observations which will be labeled x1, x2, x sub n, will come IID, independent identically distributed, from some function f of x, okay, defined by some parameters theta, okay? So our observations x come from some distribution f, independent identically distributed, and the distribution f is defined by parameters theta. Okay, and so theta is some vector of parameters of which we might have p of them. Okay. Okay, and so we define the likelihood function as the likelihood of our data. And so we say this is likelihood of some, the likelihood of, given some values of theta, is equal, and it's just going to be the product of all of our x observations. So we say x of I given our thetas. So this is just the probability of each observation, and we're going to multiply them for all of them. So this is just the product of the probability of each observation. Okay, so it's no different than saying, what's the probability of observing 10 heads in a row? It'd be 0.5 to the 10th power. That's the likelihood of your data. Okay. Okay. Because products are difficult to deal with, we often deal with the log likelihood. Log likelihood makes the likelihood turns the product into a sum. Okay, and so we call we often use lowercase or lowercase l, and then this is just the log, generally base n, of the likelihood function. Okay, so everything just becomes a sum. Oops. And it's the sum of the logs. Okay. And so, you know, the logarithm, log function is monotonic, monotonically increasing, monotonically so if we find the maximum of the log likelihood, it is the same location okay. So if we find the maximum of the log likelihood, it's the it'll be the same as the maximum of the actual likelihood. Oh, it's leap day. That's exciting. It's, back in the day, this is when women would propose to the men, right? On leap days, that was the old tradition. I mean, now it's like nobody cares, but this was there was a terrible movie called Leap Day with what's her face? Okay, a mediocre movie. Amy Adams, huh? All right, sorry, I shouldn't say terrible. I like Amy Adams in that Disney movie, Enchanted. That was a good one. Huh? I saw it Inside Out, but she's not in Inside Out. Yeah, but Amy Adams isn't in Inside. Yeah. Okay, I was like, only tangentially related because it's Disney. Yes. Okay. What am I talking about? Oh, okay. All right. So maximum likelihood estimation. Okay. Leo finally got his Oscar. What?
It's about time.
Yeah, all those Leo Oscar memes.
Oh, yeah.
No more, huh? All right. Okay. So the theta that maximizes the likelihood is our maximum likelihood estimate. I don't. So basically, it's just argmax okay, which is also, this is exactly what I wrote in words on the previous slide. Okay, so the theta that maximizes log likelihood is the same theta that maximizes the regular likelihood. Okay, so to find this, we're going to try to solve the equation where the gradient of the log likelihood is equal to 0. Okay, and this is called the score equation. Okay, so basically just like in one-dimensional calculus, we're going to find where the derivative is equal to 0. Where the derivative is equal to 0 will be our, our critical points. Could be a maximum or a minimum, hoping it's a maximum. Okay? So, Okay, and then some of which could be tomorrow's also a Super Tuesday for all of those presidential primaries. We'll see. This has been a crazy election season, man. Is this, for a lot of you, is this going to be your first presidential election to?
Well, I didn't vote last time, so.
Okay. All right. Well.
Yeah, just being like, are you voting? Being another one of those statistics.
Is that right? We'll live up to our stereotypes of young people not voting. Okay, so anyway, this is the gradient of the likelihood function is, all of our partial derivatives with respect to each parameter theta. Okay, so this is the gradient of log likelihood. Okay, and then our Hessian we're just going to call this the Hessian of Okay. All right, and so we can apply Newton's method to try to solve. I mean, there's all sorts of things we can do. Okay, but so one method to find the critical points of this is to use Newton's method, and we could apply gradient descent. We could apply any optimization algorithm we want. Okay, so one possible method. Apply Newton's method. Okay. Do you guys remember Newton's method? What do? We would say our estimates at the next iteration of, so at time t plus 1, our estimates of theta, we take our current estimates of theta at time t, and what do we subtract off? Okay, so yeah, we subtract off basically so for Newton's method, regular Newton's method to find the zeros of a regular function is you take the current estimate and then you subtract off f of the estimate divided by f, the first derivative of that, okay? Here we want to find the zeros of the first derivative, so we're going to subtract off basically the derivative, or the gradient, divided by the second gradient, okay? Or the Hessian. And so this essentially just becomes, so in kind of matrix notation, I would say the Hessian inverse multiplied by the gradient. Okay. We can also, if I just take the negative term and I put it inside here, this piece right here, okay, this is also equivalent to I of theta at time t. This is the observed Fisher information. Okay, so the formal, was that a dog barking? What was that? The observed, so the Fisher information, it's a little bit more complex, but one way to think of it is you can think of it as kind of like the negative of the Hessian. Okay, it's kind of the second derivative, or the of the function, or expected value of the second derivative of the function. Okay, so this is but that's what we have. So this would be applying Newton's method, okay, to kind of update our estimates at time t plus 1 here. Okay. All right, is this okay? Huh? This? It's just at time t, sorry. Theta at time t. Okay. All right, so we'll look at an example here, logistic regression. Are you guys familiar with logistic regression? Oh yeah? Okay. All right, well, great. Okay, so with logistic regression, basically your responses y, y1 through yn. These are all 0 or 1, okay? So essentially a class label. Okay, and then our predictors, our explanatory variables, so we're going to we'll have 1, and then x1, or I guess this would be a vector, I mean a matrix, so I should put okay, so this is our X matrix. Okay, is this all right? And then so your function looks something like that, right? And between 0 and 1, and this is kind of the different values that we've got. And so what we say is that the model, what makes it a logistic regression function, is that if we take the ratio, should say the log of the ratio between the probability of being 1 and the probability of being 0, given our x size. And the probability of being 0 is just 1 minus the probability of being 1, right? Okay. The log of this ratio is equal to all of our linear combinations of x in the beta matrix. xi1 So this is logistic regression. That's how that works. Okay, and so, and then the way, if we want to turn this into kind of the, I don't know, just a regular old thing, so we would say the probability of yi equal to 1 given x sub I, this would be, we take all of this stuff, so this would, along here would be okay, and so we can kind of define this as a function of our parameters and our input data. And then the opposite would be, I guess for completeness, one minus probability of yi equal to 1 over x sub I, which is going to be just 1 over 1 plus so we have that. Which we can say, was 1 minus okay, and then so the to kind of throw this all together, the probability of any value y sub I can be written this way. So this is going to be just because y sub I is again 0 or 1, right? Okay, so this is going to be the probability of x sub I beta raised to the y sub I times 1 minus raised to the 1 minus y sub I. Okay, so that's just how we combine those two together into a single single equation for all of this. Okay, and then so the total likelihood of our data is going to just be the product of all of this stuff. Oh man, this is too much. Okay, look at this. I'm going to cheat. Okay. And then, okay, and then so the log likelihood we'll turn all of this into a summation. Alright, and then so now we have yi times the log of pxi beta plus 1 minus y sub I times the log of 1 minus pxi beta. Okay, and then we add all of this up. Alright, and then so this simplifies down to okay. Okay, so the log of this thing ends up being y sub I times beta transpose x sub I minus oh wait, no, hang on, is that right? Let me just make sure this is what I've got written down here. Okay, yes. Alright, okay, so now we're going to set this thing equal to 0 and try to solve for it, okay? So we're going to, I'm sorry, not the log likelihood, we're going to take the gradient of this, okay? So we look at our score equation. We're going to take the gradient of this thing, set it equal to 0 to find our critical points. Alright, so we got the gradient of this is the derivative with respect to beta. Okay, now how did I do this? Okay, so yeah, when you take the derivative of a log, it's 1 over that thing, and then applying the chain rule, you multiply the thing on the inside. Okay, and so this ends up becoming basically what does it end up becoming? It ends up becoming this thing, okay? So when you put the, derivative of the log, right? So it's the log of this thing. So it ends up becoming this, and then the gradient, applying the chain rule, this goes in the numerator, and then applying the chain rule further, you multiply it by x sub I. So then we can factor out an x sub I. Okay. So this part, this is just going to become y sub I. I'm going to factor out the x sub I. Okay. So this, what's that? Am I missing a log here? I don't think so. Hang on. Okay, and then this part becomes basically 1 plus and then okay, but then I got an x sub I here and an x sub I there, so in fact the x sub I factors out, and then so here I get the sum of y sub I minus the probability x sub I given beta times x sub I. Okay, and then we set this equal to 0. Let me fix my summation sign. Not that that's any better. Okay. All right, and then okay, and then so that's our gradient, and then we will solve for the Hessian. So let's we'll copy this over. Okay, so now this thing with respect to beta. Okay, so I'm going to end up getting have p x sub I beta times 1 minus, so just continual application of the chain rule, and then x sub I xi transpose, and then the whole thing becomes negative. Okay, so this becomes this is a large matrix. This is a matrix with it's a p plus 1 by p plus 1 matrix. Okay, because we have px terms plus the kind of the intercept column of ones that we have in our X matrix here. Okay, so with our Hessian computed, we can apply Newton's method. So our estimates of beta at time t plus 1 are our estimates of beta at time t minus, okay, and then we're going to take the inverse of our Hessian at beta time t multiplied by our gradient at beta time t as well. Okay, so this is our iterative steps to find the maximum. Okay, let me see, what do I have here? Yeah, okay. So we can do that. Of course, this, this involves some heavy computations here. And so our computers can help us calculate the Hessians and the gradients at each step, okay? To kind of iteratively to go through and improve our estimates here. Okay, let's see. Okay, so computational method. Would would calculate the values of the Hessian and gradient for us. Okay. At this point, a lot of these optimization methods have already been implemented for you in these prepackaged things in R, okay, which allows you to start just applying things and just say optimize, go. But kind of at the heart of things, there is still a lot of kind of this calculus and thinking about it to figure out your derivatives and your or your gradients and your Hessians, to apply these things, right? So you figure a computer can't do the well, with Wolfram Alpha it can kind of do some symbolic manipulation and try to figure out where these roots are, but without that kind of ability, you can do these iterative steps, whether it be gradient descent or Newton's method or coordinate descent, where you just kind of give the computer some simple instructions on how to get closer and closer to a minimum or a maximum. Okay. There was one thing. Well, we don't really have time. When we talked about coordinate descent, we said you're going to minimize the function with respect to one of the variables at a time. There's a little bit of trickery there in that, well, that's a simple concept to keep in mind, and it's simple to visualize. But the truth is even minimizing based on one variable is not an easy thing to do, and you can do it. You'd have to do some mathematics to either come up with an equation to say this is how you minimize with respect to one variable at a time, or you have to use a lot of expensive computational power and say this is how you're going to search for the minimum of with respect to one variable at a time. So that's what we have there. Okay. Are there questions on this stuff? How's your homework coming along? Good? Easy? Too easy? Huh? Too easy way too easy with the code provided. So, okay. Well, I'll probably try to throw together another easy homework assignment. I don't know about easy, but another homework assignment implementing some other of these algorithms in a code form. Okay. Well, we'll end there for today. We'll see you guys on Wednesday, and that's that. Okay.